of some sort. Okay, and this I is going to be a non-empty family of subsets of S. Okay, so just to make sure that everyone can kind of visualize this, right? At the simplest thing, S is something like 1, 2, 3, and then subsets of S are the 8 subsets that we would draw out. I'm not going to draw all of them. Dot, 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 something like this. And then a family of subsets might be something like the empty set, the set with 1, the set with 2, the set with 3, like that. Okay, so this would be some subset of a family of subsets. So each item in I is a subset of S, and altogether I is that set. Okay, and so a family of subsets is called hereditary. I can't spell. I'm just gonna put E's for every vowel. That might become my banger problem for my problem-solving class. Replace every vowel with an E, which is I think what I did on this one. All right. So the hereditary property is as follows: if some subset B belongs to I, and A is a subset of B, then A belongs to I. Okay, so if you've got a larger subset of S and it belongs, all of its subsets have to belong. So that's a pretty strong property. So it's sort of like saying, hey, if this subset's there, you can take any subset of it, and then automatically that's forced to be in I. So that's the hereditary property. And then the third property, this is kind of the second property. The third property is the exchange property. And the exchange property basically just says if A and B are both in I, so if A is an element of I and B is an element of I, and the cardinality of A is less than the cardinality of B, right? So we have two different subsets. They both belong to I, but one of them is smaller than the other one. Then what the exchange property says is that there exists some element in B that's not in A, such that if we were to take the set A, add that new X into it, then this would still be an element of I. Okay? So it's kind of like this thing where, like, if we have this hereditary property, and the exchange property basically just says, hey, if you've got a smaller subset that belongs to I than another subset that belongs to I, we can go find something that's in this bigger set, and we can safely toss it into A, add it to A, and it will still maintain that property. So if you can prove, if there's some set S, maybe that set could be like edges in the graph. That set, as we'll see a couple different examples, could be like vectors, right? So anyway, if you have some set and you have this sort of property, so a few things, it's like it's always fine to remove something from a set. You will maintain that property if you remove it from the set. And the exchange property basically says, hey, if you're not as big as another set, this set will always have something that's safe to add in. So if you can prove that something is a matroid, then basically I'll get to the gist of it, is imagine now assigning weights to each element of S. Okay? So imagine that each element of S had a weight, right? And we wanted to find the matroid, right? So we wanted to find we wanted to find one of these families of subsets. So one of the subsets in here that's maximal, meaning that it's got the most number of elements. one of the things that you'll ultimately be able to prove with like the definition of a matroid is that there's a maximal size for every matroid, and it's the same. So, or each subset. So in I, like here you can see I've made it so that some subsets are size 0 and some subsets are size 1. But the ones that are size 1 are maximal, right? And so a common type of problem, maybe not common, but a problem that one could ask about a matroid is we want to find a matroid or one of these subsets that's maximal size, and then we want to minimize its weight or maximize its weight, right? And it turns out that once, and I'm not going to go through the full proof, but basically when you satisfy all these properties, you can do the intuitive sort the objects in S by weight. So if you want like minimum, small to big, if you want maximum, big to small, right? So I'll sort the objects in S by weight, start with some set T, that's the empty set, keep adding stuff to T. Okay, so you loop through the objects in order, you add into T so long as doing so creates another set in I. Okay, so if you carefully look at this, this curiously looks like Kruskal's algorithm, right? So in Kruskal's algorithm, we sort our objects from small to big, right? Minimum edge weight to maximum edge weight. We start with an empty set of edges. And one by one, we add the edge in to the set as long as it maintains the property. So the graphic matroid is that your S is a set of vertices in a graph. And it's the whole graph, really. In some sense, you need to know where the edges are. Your I is going to be the set of forests. So any set of edges that doesn't have a cycle. Okay, so that's going to be your set I for the graphic matroid. And what we can prove is that this satisfies these properties. Okay, so obviously I've defined this, the forest. This is the S is really the edges. That's probably a better way to say it. Yes, the S is the set of edges in a graph. The I is the set of forests, so it's a subset of edges. Okay, and to prove that it's hereditary, that's kind of silly, right? So if I draw a picture, here's a picture. This picture has no cycles. Well, guess what? If I were to remove any subset of edges, pretty sure no cycle is going to appear. Pretty sure you all believe me. Okay. So the last thing that we have to prove then is that this exchange property. So imagine that, here I'll just draw these 5 vertices. Maybe we'll do something like this. And then I'll draw the same 5 vertices. And then maybe I'll draw some different edges, but fewer. 1, 2, 3, 4. Maybe this is 1, 2, 3. So you can see that this does not have any cycles, and this doesn't have any cycles. So for maybe there's some more edges total. But anyway, this is some subset of edges that belongs to I. This is some subset of edges that belongs to I. You'll notice that we'll call this set A, and we'll call this set B. Okay. Maybe I'll label my vertices. We can use, here we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is something you learn probably in CS2. Did I change labels? Yeah. Oh no. Okay. All right. So I put this one as 4, and this one is. I probably labeled them dumb. Whatever. Okay. All right. So. So you learn in CS2 that if you've got a connected graph that does not have a cycle of V vertices, it's got V minus 1 edges, right? So there's an inductive proof. So what we posit is that the number of trees in this graph is fewer than the number of trees in this graph, right? So if you just kind of do there's 4 edges here and there's 5 vertices. So there can only really be one tree. And if I've got 5 vertices and 3 edges, there has to be two trees. So feel free to draw it out, but the math basically works out. You just do for each tree, v minus 1, v minus 1, right? That's probably just an intuitive way to do it, right? So for each tree in your forest, v minus 1, v minus 1, v minus 1. So when you're done, this becomes the sum of vertices, and this is minus 3, right? And that's for the 3 forests, or 3 trees that you've got, okay? So minus 1 for each tree, essentially. So that means that this guy has more trees than this one. It's got 2, and that one's got 1. So that means if this one's got fewer trees than this one, there must be an edge that connects 2 vertices that are not connected in this picture. Okay. So because that's the case, there's no cycle in this guy, this little thingy. There's no cycle in this little thingy. So me adding this edge is going to be safe. It's not going to create a cycle. So that proves the exchange property. This might not have been the greatest example, but if you draw a bigger example, you'll always find some edge in B that's connecting 2 different trees in A, and then it's safe to add that. Okay. So once we prove those things, then that basically is the proof of Kruskal's. So in Matroid theory, you can basically show, because of the exchange property, I'm not going to go into the full details, but the exchange property is a pretty powerful thing. It basically like says, hey, if I'm building something, there's always going to be something in here that I can toss in. So basically, if I'm going to toss something in, I may as well toss in the biggest weighted thing, right? Consider that, or the smallest weighted thing, right? So I have the formal proof written. It's from CLR, but intuitively that should make sense to you. Is that basically this idea that I can start with empty, and if there exists any maximal subset that includes an element, then it'll be safe for me to add that element in first, and then the next one next, and so on. All right. Now, yeah.
So why is it that we have to draw an edge that connects 2 different trees?
I mean,
I guess I don't see.
You don't. Well, you would have to draw an edge that connects 2 different trees, because if you draw one more edge in a tree, it's going to cause a cycle.
Yeah.
So you want to prove, like to specifically prove this property, you need to show that there is at least one edge in here that when you add it into here, doesn't cause a cycle. And the simplest way to prove that,
one exists.
Yeah, and the simplest way to do that is just to look at the fact that there's just a different number of trees in both pictures. And if there's a different number of trees, there just has to be something that connects, right? Kind of like a pigeonhole.
It doesn't have to be every edge to be.
No. There might be some edges. There might be some edges in, like this picture's not a great picture, but there might be some edges. Like actually 2-4. 2-4 is an edge that, like, had I added it in here, it would cause a cycle.
That's what I was wondering.
Yeah.
That's a good picture.
So, all right. So anyway, a weighted matrix, as I mentioned, is that each object in S has assigned a weight, and then we want to find the maximum weight independent set. So these are independent sets essentially, and the largest independent set. And basically, the algorithm is down here for any matroid. All right. And the proof basically is that if you've got something suboptimal, basically I can swap it out. Do you see what I'm saying? I can swap out something of lower weight and toss in something of greater weight. You know, and that exchange property is pretty powerful that way. When they show the proof for MST, basically what they say is, hey, look, here's some stuff that's connected. Here's some stuff that's connected. Consider all the edges that are between these 2 sets, right? And if this one, like, if you're doing for minimum spanning 3, if this one has like weight 3 and this one has like weight 7, let's say your MST connects these 2 with this 7, well, it's pretty easy for me just to get rid of that 7. I can add the 3 in to make the cycle, and then erase the 7 and get rid of the cycle, right? So that, like, when they show that picture, probably most CS2 books, they have this picture. That's basically the same exact thing as the exchange property. All right, so now the question is, well, what are some other possible matroids other than the graph matroid? And I think Jacob's probably going to do more of these, but I'll at least show you a few of them. So imagine vectors in n dimensions. Okay. So, and then the goal is like their independence in vectors meaning that they can help you get to new places that you couldn't get to. Obviously, like in 3 dimensions, it takes 3 vectors to reach anywhere you want to go, something like that, right? So these 3 are independent, and then like if you have something like this, right? Something like this is not independent, right? So you wouldn't be able to add this guy into this set because now the 3, 4 can be created from some linear combination of 1, 0, 0 and 0, 1, 1. Okay. So if you imagine that S is a set of possible vectors that you can make in n space, and I is any subset that's independent vectors, meaning that no vector in the space can be created by a linear combination of all the other vectors in the space, right? Then that also forms a matroid, okay? And so that's an example of another matroid. So if you ever had a problem where you had like these different vectors and you wanted to combine some set of vectors, each vector had like a cost of some sort, and you had some choice. Maybe you had like 20 vectors of size 3 or whatever, and you wanted to choose the minimum possible set cost-wise so that you could still create vectors to reach everything in 3 space. You could do it exactly like this. You sort the objects from smallest to largest, right? And then when you're considering a vector, you just ask yourself, hey, when I add this in, does it keep the vectors independent or not, right? Which you can do Gaussian stuff to basically, if you get all zeros with the Gaussian stuff, then the answer is no. Yeah?
So specifically minimum cost basis, not just minimum cost subset, not minimum cost independent subset, right?
I think they're still independent, right?
Well, yeah, but you want like the largest.
The largest one.
Yeah.
Yeah.
Which is a basis, not just any.
Oh, gotcha. Yeah.
A basis of the matrix, not a basis
Right.
of the.
Because in substance you could say, oh, nothing.
Yeah.
Yeah.
Which.
Right. That's what I mean. Yeah.
And similarly for the graphic, it's the minimum size or minimum cost.
Maximal
basis
size
of the matroid, which is a spanning tree, which is
yes.
spanning tree,
Yeah.
so.
Yeah. Like of these subsets, the largest size subsets.
Yeah.
The
Which
one
are
of
all
minimum
spanning.
cost. Maybe. Yeah. I don't know. Yeah. Of the largest size subsets. What is the minimum cost? The min or max cost. Okay. All right, so we got those 2 matroids. The third one that I have, this one's kind of interesting. I don't know how someone would make a problem about this, but so let S be some set, and let a partition of the set S be S1, S2, S3, ... Sk. So you can think of S, maybe we can even think of S as the programming team, and S1, S2, S3 are the teams of size 3. And then I could be the following set. The set of all A is a subset of S, such that when we intersect A with S of I, the cardinality is at most 1. Okay. So this is basically like saying take no more than 1 student from each team, right? And it's very clear what's the maximal size of any object that you would have in I. What's the maximal size of the number of elements in a subset of I?
Okay.
Yeah. Okay. Yeah. Because the best you can do is grab 1 from each, right? And hopefully you can intuitively see that this is hereditary, right? Like if I took 1 person from 6 out of the 9 teams, you could remove any of those people and we'd still have one of these sets. And then for the exchange property, if I have like 6 people from 6 different teams, and someone else has like 4 people from 4 different teams, well, there's at least 1 team I have somebody from that you don't have somebody from, right? Pigeonhole. And so then whatever person I have from that team, well, you could add them in. All right. Okay. And then the last thing I'm going to do is I'm actually going to do a problem. I don't know. I couldn't find this exact problem on a judge. Otherwise, I would have submitted it. But the problem is as follows. I could probably. Let's see here. I didn't want to. I guess I can erase this. This is not useful. I think I can fit everything I need to for the problem over here. So we have unit tasks. That's marker's not good. Let's try. we have one processor, and each task has a deadline. Okay, so we might have like, I'll just write down the deadlines. Let's say it's like 6, 2, 2, 4, 1, 4, 3, 8, 7, 2, 3. So these are some tasks. And those are the deadlines. And each one takes 1 minute, or 1 unit at a time, whatever. And each task has maybe an amount of money that you get for it, right? So let's say I get $70 for finishing this one, 30 for this one, 10 for this one, 40 for this one, 50 for this one, 30 for this one, 60, 70 again, 25, 35, and 30, let's say. Okay. And your goal, obviously, is maybe you can't schedule all of these things. I've got all the deadlines are less than or equal to 8, but there's probably more than 8 tasks there. So I can't schedule all of them. I want to pick some subset of these things to schedule that gets me the most money, right? So I can put something from time 0 to 1. Like if I'm going to schedule this one, for example, I have to schedule it. If I were to do this one, it has to go in minute 1 from time 0 to time 1, because then the deadline's up. Okay. So it's pretty easy to see that if I've got 1 with deadline 1 and 3 with deadline 2, only 2 of those, at most, only 2 of those 4 will occur. So I want to prove that, so let S be the tasks. S is going to be these tasks. I is going to be any subset of the tasks that there exists a valid schedule for. Okay. So I is hereditary. If you've got some tasks scheduled, like hey, this happens starting at time 0, time 1, time 2, time 4, whatnot, then any subset of that, I can just remove anything, and that's not going to tax the processor gets 1 more minute of break or whatever. So hereditary is very easy to prove. Okay, so now let's prove the exchange property. The exchange property is maybe a little bit harder to prove. So imagine that we've got 2 competing schedules, A and B, where B has more valid items. So maybe B's schedule looks like this. I'm just going to write the deadlines from here, not when they actually get processed. Okay. So let's say these are the deadlines for B, and then for A, let's say it's like 1, 3, 4, 5, 7. So what we want is we want the last point in time, max time, where the number of items for A is greater or equal to the number of items for B. We know that they start both at 0, so there must be some point where this is true. So we can see that the max time where A has finished as many items as B, in the sense that by here is time 4. Because at time 4, actually, let's see here. At time 5, time 6 is going to be when B is bigger than A. So time 5, actually, there we go, that's a better run. Time 5 is going to be the last time where NA greater or equal to NB using the deadlines, like that. Okay. So at this point, we know that at the end, B is going to be greater than A, and then we call this time K. So we know that at time K plus 1, what's going to happen? So at time K plus 1, NB strictly greater than NA, right? So that's like the exact time. And if this is true and this is true, that means that schedule B has more tasks with deadline K plus 1, right? There has to be some crossover point. And since it has more tasks with time K plus 1, right? What we know is that at least one of these tasks is not in this schedule. And if at least one of these tasks is not in this schedule, and we know that this is a valid schedule, and 6 is the last endpoint, so we have full freedom from time 0 to 5 or 1 to 6, however you want to look at it, to insert it. one of these, A, doesn't exist in this schedule, in this case both of them don't, and B, you have to be able to insert it because there has to be a free time here because all of these are being done and we've got the full freedom of time. So since that's the case, our algorithm's simple. We just sort from max to min in the red values, how much money you get per task, and then you add it into the schedule one by one if you can. So how do we know if we can add it into the schedule? So there's probably lots of ways to do it, you guys can figure it out, but my simple idea was that you keep a tree set of the times that you're free, right? And so then I schedule something at 6. So in my tree set, I remove 6. I schedule it at the latest possible time. So, and then what's the next highest one? This one right here, I schedule that one at 8. So my tree set no longer has 6 or 8. When I query the tree set, I say, hey, what's the largest number less than 9? Okay. And then what's the next number? Like 60? I say, what's the greatest number less than 4? It's 3, and so on. Right? So when you get a query that says, hey, there's nothing there, right, that means you skip that one. So that should run like in login. Yeah.
Is it true that Matroids are very, because like based off of this and the MST example, what I'm gathering is that Matroids seem to be very useful in greedy problems.
Yes. Yeah. It's a framework for greedy. Correct. Yeah.
Do Matroids ever come up in implementation specifics, or are they always used as proof?
It's a proof.
And then okay.
Yeah. The implementation is going to be specific. So some things are like trivial, and then some things are harder, right? So probably the hardest thing to code, obviously sorting tends to be pretty easy to code, right, in the algorithm. Usually the hardest thing tends to be making sure that when you add something in, like in terms of runtime, when you add something in, making sure that it's valid to add in and you maintain that independence, right? So for example, in Kruskal's, we need to make sure we didn't add a cycle, so then all of a sudden we got to introduce this disjoint set. Here, you gotta do some linear algebra mumbo jumbo to make sure that you can't create the thing, right? Here, I had to do the tree set nonsense to schedule stuff, right? So that's really gonna be this, so long as doing so creates another set in I, that's probably gonna be the hardest implementation bit, and that's gonna be problem specific.
Right.
So, all right, and now we get to learn how to intersect these things.
Thank you, Arup. So yeah, these three Matroids are like pretty common. All the problems that I've solved have used these Matroids. So this is the graphic Matroid. This one is known as the linear Matroid, and this one is known as the colorful Matroid. So Arup had a really nice way of strongly defining this, but the way that I think about it is you've got a bunch of balls and they all have colors, and you want to pick any subset of the balls is valid if they all have different colors in your subset. And that's actually the same thing as this. You have the elements, you partition them, and then you imagine all the things in S1 are the same color, all the things in S2 are a different color, but they're a different color from S1 but the same color within the S1. So yeah, you want to pick. So this is the colorful Matroid, the linear Matroid, and the graphic Matroid, and these are pretty useful. Any questions on those Matroids? Okay, another piece of terminology is that any subset that belongs in I, so any element of I, that's often referred to as an independent subset of S, which is the ground set. S is a set of elements. A subset could be either independent, which means it's a member of I, or dependent, which means it's not a member of I. And the terminology comes from the fact that a matroid is actually a generalization of this, which is linear independence. So in a vector space, linear independence has all these properties. Of course it does, because a matroid's I believe, my understanding is that they were defined on we would like to generalize the properties of linear independence. And so that's what's going on here. But with group theory, okay. So let's talk about a problem. I'm gonna erase this. This is a problem as well. So the problem is as follows. You're given edges, and all the edges have a color, and you want to find a spanning tree. There's no minimum weight or whatever. We're not gonna get to that yet. We just want to find a spanning tree such that every edge is a different color. That one back. Okay. So, okay. Any questions on the problem itself? Zach?
So there's like between any two sets of vertices, like there could be on most one edge, and it's one color, right? Or can they be like multiple edges between the same two vertices?
I mean, like, so you like a spanning tree is a subset of all the edges in this graph.
Yeah.
That spans the
Can there
graph.
be multi-edges is the question.
In the original graph.
It's not there. It doesn't, or like, I guess there could, yeah, there could be multi-edges in the original graph, sure. It doesn't, there can also be self-loops. Doesn't really matter.
Can you say the problem again?
Yeah, you want to find a spanning tree. So you're given a graph, which is a set of edges, but all the edges also have a color. And you want to find a spanning tree such that all the edges are different colors. Okay. And we don't care about minimizing, we just want to print out the spanning tree. Okay. So what this boils down to, or does anybody have an idea of how we can use the intersection of two of those matroids to solve this problem? Right?
You want to intersect the graphic matroid and the colorful matroid.
Yeah, exactly. So Matroid intersection is defined as you've got two matroids and they both have the same ground set. This is key because otherwise it doesn't really make sense to intersect them. They just have different stuff. So two matroids with the same ground set but different independent, like different I, which is like different subset of the power set, which are independent. The intersection of that matroid is all of these subsets that are independent in both I's. So like I1 and I2, if you have like M1 and M2, right? So, and for this problem specifically, we want to find a basis of that intersection. So a basis is this, which is any subset, or like any element in I that is of maximal size. Because there exists a maximal size in I because there's a finite number of things. And so all of the elements of that size, of that cardinality, are bases. And we want to find basically like a based subset of this intersection. Okay, and just one second. Again, a basis of the graphic matroid is a spanning tree because, well, like if we have a subset of edges and it's a forest, but we know that this is the maximal size, which means we can't find another edge that we can add to this to keep it a forest, then that means that the number of trees must be 1, which means it's a tree. It's a spanning tree. All the nodes are in one tree. And similarly, if, well, we don't really necessarily care about the colors, but we know that in the graph, for there to be a colorful spanning tree, there has to be like at least n-1 colors. There could be more colors. So we don't actually need to reach a basis in this matroid, right? But we do want to hope that the basis of the intersection of the two matroids is of size n-1. Otherwise, we're kind of screwed, right? And okay, so now any questions about what this, any questions about anything I've said so far? Quinn?
Yeah, sorry, what was the ground state again? Just like
It's this.
set?
It's a set of objects that we're working on.
Oh, okay.
So it's just like edges.
Yeah, in this case, it's all the edges of the graph that have their color and their u and v. So like when we're given input, we're given 3 integers to define an edge, which is like u, v, and c, the u, v, and color. Any other questions? Okay, so we want to find a basis of the intersection of two matroids. So let's just start by just like sending it. We're gonna pick, well first I'm gonna go ahead and label, I'm gonna label these edges. I'm gonna label this edge 1, 2, 3, 4, and 5, okay? So let's just read in the input and we can assert, like we can check if an edge is independent. It's like we're gonna maintain a subset of the edges, which will always be at all times independent in both matroids, right? So we will maintain a subset of the edges that is acyclic and also like doesn't have like is also colorful, doesn't have like repeated colors, right? So we can pretty easily check if we can add an edge to this set by doing 2 checks. First of all, do we have any of these color? If no, then we're cool. And second of all, is this like, are these 2 things in the same disjoint set? If they are, then we can't add this edge because they're already joined. If they're in disjoint sets though, then we can add this edge and we're not going to cause any cycles. Are we all on the same page? Okay, very easy to check if we can add an edge. So let's just read in the input, and if we can get it, let's do it. So we're gonna add 1. That's let me get like a different color here. So we read in edge 1. We can add this. Are we on the same page? We can add edge 1. Okay. We read in edge 2. Can we add this? Yes or no?
Yep.
Yes.
Okay. We read in edge 3. Can we add this? Yes or no?
Nope.
No. We lost. If we read in edge 4, can we add this? Yes or no?
No.
We read in edge 5. Can we add this? Yes or no?
No.
Okay. So we're done. Submit. Hold on though, because we could all look at this graph and find some colorful spanning trees, right? So we have not reached a basis. All right, give up. I'm just kidding. Okay. So let's go ahead and write all the elements of the ground set on the board. We're gonna write them on the left if they're in our set, and we're gonna write them on the right if they're not in our set. So let's go ahead and write 1, 2, and then 3, 4, 5. Okay. So now there are going to be some elements that we can add. So let's go ahead and define M1 is equal to the pair of edges and we have some like independence I1, and this is the graphic, and M2 is the colorful, based on I2. Okay, so now we're labeling these. So let's go ahead and find which elements that we could straight up add to our set, and M1 is still happy. We don't care about M2. That guy is dead to us. We're just finding the elements that M1 would accept. Okay, so if I added 3, is M1 still happy?
No.
No. I'm also going to define this as Y1. Okay, so Y1 does not contain 3. Does Y1 contain 4?
Yes.
Yes, because if we add this edge, it's still acyclic. So let's add 4. And similarly, 5.
Yeah.
Yes, same thing. Okay. Let's also define Y2 in the same way, but for the colorful matroid, we don't care about the graphic. So Y2 is 3, but can we add 4?
No.
Why?
Is our green blue?
And can we add 5?
No.
Because?
Q is also green.
Okay, so we can add 3 because it's a different color, but not 4 and 5.
So you're adding those independently? You're not adding all of them?
These are just, we're not doing anything with these yet, but we're saying Y1 is the set of all elements that aren't in our independent set, but we could add, and M1 would still be happy. And Y2 is a set of all elements that aren't in our subset, but if we added them, M2 would still be happy. Okay? Sathik?
And is it true that they would not have any common elements because it would be...
Well, it's not always true. But I guess like if we set it up with our greedy, then yes. But that is exactly what I was going to get into is what happens if these sets have a non-empty intersection.
Or non-empty?
Yeah.
You would have added it.
Yeah, I was just.
But like, let's be exhaustive here. So yes,
Okay.
if they had a non-empty intersection, then we could just straight up add that element because adding it, both the matroids are happy. So cool. And we'll get to why, because like sometimes you'll make a relaxation and then you can just straight up add a thing. So that's why we have to be like strict about that. Okay, what if one of these sets is empty?
There's no
It means you can't do it.
Quan?
We either have a spanning tree or all like n-1 colors.
Exactly. Well, not n-1 colors. You have like all the colors, right? Yeah. So if one of these sets is empty, then you either have a spanning tree or like the graph was disconnected in the first place, which is stupid. But yeah. So either there is no edge that you could add and maintain acyclicity, or there is no new color. We have all the colors, so there's no way for us to like continue adding edges. So what this means is that we have reached a basis of the intersection of M1 and M2. Because this is the maximal size set. There is no bigger set that is still independent in both of these. Are we on the same page? So if this is the case, if Y1 or Y2 is empty, we're done. And we should just check if it's size n-1, and if it's not, then we print out no. If it is, then we print out yes, and we print out all the edges that are in our set, because we know it's all good to go. But the general case, what if they are both non-empty, but they don't have an intersection? Are we screwed? No, we're not screwed. Okay. So let's now define more sets. We're going to have E1 and E2. Okay. I'm actually going to use a different color for E2 because it's going to get a little messy. Brown's going to be good. Okay, yeah. All right. Well, I'm not going to draw them here because they're not really. They're kind of big. It's a graph. Okay. So for E1, we want to say, okay, for each element in our independent subset, for each element not in our independent subset, if we deleted this and added this, is M1 still happy? Okay. So E1 is, can we exchange, we're going to draw an edge, if we can exchange this element for this element, and M1 remains happy. Okay. So 3, we couldn't just straight up add to M1. But if we deleted this edge, could we now add this edge?
Yeah.
Yes.
Yeah, so let's do that. If we deleted 1, could we add 4?
Yeah.
Yes.
Sure, yeah. I mean, we could have added 4 in the first place, but we still can.
We're only
If
talking
we,
about M1.
huh?
We're only talking about M1, right?
Yeah, we're only talking about M1. Similarly, if we delete edge 1, could we add 5? And M1 is still happy. We don't care about colors.
Yes.
Okay, so that's cool. The same is true for 2.
Yep.
We're not lots of generalities, the same thing, so let's just do that. Okay, so E2 is the same thing, but for the colors instead. So if we deleted 1, could we add 3?
Yes.
Yes. If we deleted 1, could we add 4?
Yes.
Yes.
Because
Oh,
we're getting
yeah,
rid of
you're
our-
deleting it.
Oh, you're getting rid of it.
You're deleting it.
Yes.
Yeah.
So if we deleted 1, we could add 4.
You just can't.
Wait.
Okay, right? Because then we would no longer have a blue.
Is
So
one blue?
remember, these oranges are just like noting what's in our set. I'm gonna erase these. That was just like, I should have like circled the numbers instead of like drawn the edges. But yeah, the graph looks like this. So if we had, like currently we have 1 and 2, right? Because that's what's over here. So we've got these. If we deleted 1, then we could add 4 and the colorful matrix would be happy. Because we know we removed the blue, so we can add another blue. But if we remove 1, can we add 5?
No.
No,
It's
because
already green.
we're removing a blue, but we still have another green, so that's like kind of bad, right? Okay, and then 2, if we remove 2, can we add 3?
Yes.
2 to 4?
No.
No.
No, 2 to 5? Yes, okay. So now, I'm gonna go ahead and circle on this side, y1 and y2. So y1 is 4, 5, and y2 is 3. Okay. So now we know that, okay, so there's a guy's proof that says if these are both not empty, then we will be able to add something to our matroid by perhaps, or to our independent subset, by perhaps removing some other stuff and adding some more stuff, right? So we can't trivially add 1, but so we know we're gonna we'll remove 1 and add 2, and then we'll have gone +1. That's cool. So that's someone's theorem. I think it's like a trivial property of this, or like trivial extension of this property or something like that, but it's fine. What?
What's the theory exactly?
If you have y1 and y2 and they're not like empty, then you will always be able to increase the size of your independent subset. So you're done once they're empty, and you're not done once they're not. Okay. So let's just go ahead and add in 3. Okay. Let's just add that guy. Okay. So we know that 3 was in y2, so M2 is still happy, right? We added 3, so now our subset is 1, 2, 3. M2, chilling, relaxing, okay? But M1, oh no, because it wasn't in Y1. So M1 is really he's kind of sad right now. He's dependent. We don't. This is not good, right? So, man, I wish that we had a way of determining what kind of elements would be addable if we, or what were the elements that we would have to remove if we added 3 that would maintain happiness in the other matroid.
1 or 2.
We do!
It's the what is it, the blue edges?
The incoming enemies.
Yeah. So it's this blue edges, right? Because the brown edges were for M2. So the blue edges say, oh, I could have deleted this guy and added this guy, and we'd be happy. So let's go ahead and add this guy, and now we know that we have to delete some guy that was connected to it by a blue edge, because then we'll know that both matroids are happy. So let's just go ahead and do that. I'm just gonna say we'll use 1 for now. Okay, so we're adding 3, and we're going to say, let's remove 1. Because, okay, so now both matroids are happy. Are we on the same page about right now? We removed 1 and added 3, and we know that because there was a blue edge before, M1 is happy, and we know that because 3 was in Y2, M2 is still happy. All on the same page? 1?
And it doesn't matter which edge we do, like it could be either 1 or 2 because we could just do the same process again.
Well, we're just asserting that right now they're happy. This is like, I haven't picked these with any structure. I'm just demonstrating this example that we can add some element from Y2, and then we can use some edge from E1, and now both of them are happy. If we replace 1 with 3, both matroids are happy.
Yeah.
Okay. But now we haven't actually helped ourselves out, because all we've done is the size of our independent set is the same, right? We just added one thing and removed another. It hasn't changed. But now 1 is gone. So we can use a brown edge and take something else, because M2 is still happy, right? Or M1 is still happy, right? So if we find an edge that goes into an element of Y1, then we know that M1 will still be happy. So let's go ahead and use a brown edge, which means that M2 will still be happy after this exchange. But we've already deleted 1. So we can just add this for free, right? Because this guy's already gone. 3 kicked him out. So we can add this for free. So this is cool. Now, we have actually found a way to increase the size of our independent set. We delete 3, we add 3, we delete 1, and we add 4. So we've added 2 and deleted 1. We got a +1. So this is an augmenting path. And if we are able to find a path from an element of Y1 or 2 that goes, it only uses blue edges going this way and only uses brown edges going this way. If we can find a path from an element of Y2 to an element of Y1, then we know we've done some exchanges, and all along the way, both matroids are still happy, and we've started in a place that M1 was happy, and we ended in a place where M2 is happy, and along the way we maintained happiness, independence. And so this means that we found a path that adds one more thing that it deletes. So in this graph, there is an augmenting path from 3 to 1 to 4. There's also an augmenting path from 3 to 2 to 5, et cetera, et cetera. There are many colorful spanning trees of this graph. There's 2, I guess. Whatever. Yeah. Okay. Any questions about this algorithm?
I don't know if I'm jumping ahead here or not, but if we wanted to do min or max now, can we sort both of our columns?
No, not quite. So min and max, yeah, we can get there really quickly. We can weight the edges by the change in cost to our independent set. So if this guy had a weight of x and this guy had a weight of y, then we know that when we add 3 and remove 1, we're going to get plus x minus y, right? So the weight of this edge is x minus y.
Oh, okay.
And then we want to run Bellman-Ford to find the shortest path from an element of y1 to any element of y2.
All right.
And there's a theorem that says, yeah, it's related to the theorem that Arup pointed out, except it's a lot more complicated because we're doing this intersection algorithm. But yeah, there is a theorem that says you use Bellman-Ford, so you find the shortest path, the shortest augmenting path, and that's going to be good to go. Quit?
What is an augmenting path?
An augmenting path is a path from an element of y2 to an element of y1 that uses blue edges going this way and brown edges going this way, and we know that any augmenting path is going to increase the size of our independent set by 1. Jacob?
Does this rely on you having done that greedy process before, or do we then rebuild this graph again to find the next augmenting path and so on?
Yeah, we don't have to have done that greedy process before. I just needed to
just
have,
to be able to
have a
draw
reason
something.
to have a graph.
Sure.
But yes, so we're going to do this. We're going to increase the size of our independent set by 1, and now once we've done that, the graph is completely screwed because now we have some stuff on this side and some stuff on this. It's not by parts totally messed up.
There's no nice way to maintain it.
Yeah, there's no nice way to maintain it. We completely discard it. We build it again by doing this n squared kind of thing of saying for this, can we add it? Or can we exchange for this, can we exchange? And we also compute y1 and y2. We run this DFS and yeah. So Matroid Intersection is not fast, but it is correct. There is a guy's theorem I don't know. There's a theorem that was like pages long that says you're never gonna get into a kind of like local maximum where you would have to like just remove something so that you could add like more stuff. It's based on this property that like you're never gonna like be in a place where like I can't add any more stuff like or with any exchanges, but I know there is a basis higher up because like
It's like exactly this.
yeah, I guess it is exactly the same, but it's like pretty complicated when you start having like the independent set change. But I guess that's just like for rigor. But if that's intuitive, then we can just like go with it. But I'm just gonna say that's the guy's theorem.
Could you ever find some path that goes through like a bunch of things and then you can remove like a bunch of things and then add a bunch of things like in one like move?
Yeah. So this path just happened to be of like 2 edges, which means we like did 2 swaps, which ended up in adding. But yeah, we will generalize this because not every element in this will be a member of Y1 or Y2, and so there might be paths that go through like if we have like another edge like 6, and I don't know, like maybe the edge 6 is like a blue edge of these guys, and this is 6, and neither Matroid is like perfectly comfortable with this edge. So it's not a member of either, but maybe you need to like add it to perform an exchange. So your augmenting path might be from like 3 to 1 to 6 to 2 to 4. And then what you would do is you would add 3, remove 1, add 6, remove 2, and add 4. And then your independent set still increases in size by 1. So your augmenting path could be quite long, but the idea is the same. I don't think this is an augmenting path, but you get the idea. Jacob.
Can you show either why we wouldn't have or why we wouldn't want to select an augmenting path that goes from like Y1 to Y1 or Y2 to Y2?
Yeah, so if we had an augmenting path, I mean, you couldn't.
Why not?
So yeah, so we know like the only reason it's a valid endpoint is because okay, like yeah, I guess when you have these multi-edges, then you know like you can do like just like straight up exchange and both matroids are happy. But if you have an edge like this from 2 to 4, when you perform this exchange, like both of them might not be happy when you do this exchange, only one of them, right? But we know that if we can do this exchange, but also it's like this, like the brown was already happy anyway, then you're good, right? And so like, does that make sense? It's like, Y, this is Y1, brown was for Y2, so whatever. But yeah, I don't know if there's an example in this graph, or I guess yeah. If it looked like that, then they would just be straight up like you would have the intersecting Y1 and Y2. But yeah, the reason is we have to go from Y1 to Y2 because Y1 is a way of performing an exchange in like remember both of these matroids are happening, but the edge like either a brown or blue edge only maintains like independence for one matroid. So when we perform this swap, we still have to make sure that both matroids are still like cool with it. And we know that like if it's an element of Y2, then we don't have to concern ourselves with the matroid 2 because we know it's happy just straight up adding this element in the first place. So we only have to concern ourselves with M1, which is why we only look for blue edges when we perform an exchange for some element that's already in Y2. And the same thing can be said with Y1 because they're general. Eddie?
So like the blue edges are exchanges that preserve M1-ness.
Mm-hmm.
But then you can add in 3 because it just, then you know for a fact that it preserves M2.
Yeah.
So you swap it with something that preserves M1 and then you like keep going.
Yeah.
Oh, okay. So and if you had both edges pointing to 2 things that were in the same set, that would mean that like swapping this element in preserves what like M1, and swapping the element for the other one also preserves M1 and M2, and so it like would have been included already in one of your sets.
It would have been included in both.
Well, this doesn't necessarily rely on Y1 and like Y2 having no intersection though, right?
Well, like you're saying, if you find an augmenting path from 4 to 2 to 5 or something like that.
Yeah. Which like that might happen at the beginning of your algorithm, right?
But you wouldn't. But the thing is, you wouldn't be done.
Yeah.
Because like when you add 4 to 2, sure, that's like you're maintaining coolness in both matroids. But when you add 5 again, then now you've destroyed the matroid. So the only way to like do like an actual addition, like because like you can go from 3 to 1 and both matroids are happy, right? But we haven't actually helped ourselves out. Mm-hmm. To help ourselves out, we want to continue. So we want to add another edge. We want to like add another thing, right? So, but we need to make sure that when we do that, we don't like screw up both matroids. Because when we take an edge, we're only guaranteeing that that edge maintains like independence in one matroid. But we know that these guys are sinks for another, for like some matroid. Like if an element of Y1 or Y2 is a sink for one of the matroids, because it doesn't, you don't have to make sure that the edge that you just took maintains independence, because it just is. That's like the definition of these sets.
Okay. So we're not like enforcing that it goes from Y1 to Y2. That's just naturally something that happens. Like
well, we are like when we run the algorithm, we have to find a path from Y1 to Y2, because then we know that flipping everything along that path, we end up on the same side that we started, which means we increase the size of the matroid, or the independent set. So like add, subtract, add, subtract, add, subtract, add, subtract, add, subtract.
Yeah.
We want to start and end with an add, because that means that we have like a +1. So we have to end on this side. But when we like do an add, we need to make sure that we didn't like screw up the other matroid that wasn't like happy with his edge. And this graph is pretty dense, but you could like these edges are more common, where an exchange is cool for one matroid but not for both. Similarly, that's just you get the idea. Okay.
And I think like another way of looking at it is the process in reverse would also work. Like you could start at 4 and swap it for 2, but then because you have to maintain, you could go to 3, but you're not allowed to go to 5. So in the algorithm, you have to know that you can't take the 2 to 5 edge, but you can take the 2 to 3 based on the colors.
Gotcha.
Alright, let's let that. No, that's not it. That's not everything. We're gonna go through some problems. What time is it? I don't know.
Alright, you have 3 minutes.
I do? Okay. Alright.
Oh, I thought we were gonna end at 12 now, or 11.
Are we? I'll go double check.
That's what
Yeah, I thought the email said.
Yeah, I told them that we'd be done at 12.
Okay.
Okay. Alright, so, yeah, okay. So I've got a couple problems. One of them is, it's like from a Petrozovos 2018 or something like that. So the problem is as follows. Alice and Bob are playing a game, as they do. They're gonna play Nim, but Nim is too boring. Already solved, XOR, all good. Nim is too boring. Let's get a little funky in here. So we've got some boxes. They've got boxes of numbers, and each number represents like a pile of Nim. So they're gonna play multi-pile Nim. What they're gonna do is Alice has some boxes, and these are Alice's boxes, and Bob has some boxes, and these are Bob's boxes. What's gonna happen is Alice is going to go through each of her boxes and pick out one number from each box. Bob is gonna do the same, and now they're gonna play multi-pile Nim on like these like piles that they've done. But actually, before they go ahead and play Nim, Alice is gonna cheat, and she's gonna take a subset of the piles that Alice and Bob have chosen, and then they're gonna play multi-pile Nim on that. So let's say that Alice has some boxes, and Bob has some boxes, and maybe this box contains like 1 and 2, this box contains like 2 and 2, whatever. This box contains 3, this box contains, what's the XOR of 2 and 3? It's 5. Okay, so Alice, or 1 and 2 and 3, it's 4. We're gonna go.
Wait, what's in the box? 1?
Can you have as many numbers or just up to 2 in each box?
I screwed myself over here. What have I done? What have I done? 4, and what's 3 is 7. Okay. Alright. So let's say that Alice picks a 1 from this box, a 2 from this box, and Bob picks a 4 from this box and a 7 from this box. So if they play multi-pile Nim, Bob wins. Yeah, Bob wins, right? But Alice, she's a stinky cheater. So before they go and play Nim, she's gonna pick a subset of these. So she's like gonna delete some of these things, right? So Alice cheats and she removes 2. And now Alice wins, right? So, yeah, we want to make sure that this is always possible.
Yes.
After 0, she just picks removes one of the boxes.
Yeah, or whatever it is. Okay, I forget the flavor text exactly, but yeah, Alice is gonna pick her stuff, and now it's Bob's turn. He wants to pick some stuff such that there does not exist any subset of the stuff that he picked, such that the XOR is 0. So I guess in this case, like he would be fine. I guess Bob gets to go first when they play Nim. So Alice would be happy keeping this set because that means Bob goes first. That's what it is. But Alice gets to cheat and do this subset stuff, right? So we need to make sure that all of these things that we can't have a subset of XOR 0 because then Bob would lose. So Alice has already made her picks. We know her picks. She's picked 1 and she's picked 2. But Bob gets some choices because maybe this box contains like 4, it contains 2, it contains 3, it contains 1, and maybe this box contains 7, it contains 4, right? So Bob might be able to pick some stuff from these boxes such that he loses, which means that Alice can find a subset such that the XOR is 0. But he also might be able to find a subset, find an element to pick from each box such that there does not exist a single subset that has an XOR of 0. And you want to figure out if Bob can win, and if so, print out which elements he should choose.
Empty disallowed? Like empty subset?
You must choose exactly one element from each box.
No. Oh, so but when Alice chooses?
No, the empty set is not allowed.
Okay.
Sorry. Questions on the game?
What is Alice's operation?
Alice.
Her cheat operation. Right?
Her cheat operation is we have all the numbers that we're about to play multi-pal nim on, but she's going to delete some of them.
Okay. She's going to delete some.
She gets to delete however many she wants, not all of them, and she wants to make it such that the XOR is 0.
Wait, she can delete any of them or just her?
She can delete any subset of any of them, yeah.
As long as it's not all of them.
As long as it's not all of them. And yeah.
And the question that we're answering is what?
The question that we're answering is, Alice has already made her moves, but we are Bob, so we want to make sure, we have to pick exactly one number from each box, but we need to do that in such a way that there does not exist a way for Alice to win the game.
Okay, so Alice is not actually making decisions about the box at this point.
No.
We're just giving Alice
as
input. Okay,
yeah.
gotcha.
Right. And Bob has to make his choice such that Alice can't win.
So if Alice's set of boxes that she chooses has a subset of XOR 0, Bob is pretty much screwed, right?
Yeah, I think so. Any questions about the game? All right, any ideas how to solve this with Matroid Intersection? We need 2 Matroids such that a basis of the intersection of those Matroids has the solution to the problem. Daniel.
So we need to make sure that we don't have in our set a subset that XOR is 0.
Mm-hmm.
So it's we need all our stuff to be linearly independent.
Yep.
Under XORs.
Under XOR, yeah. So we've got some bit vectors, and we know that no subset has an XOR of 0 if they're all linearly independent. But if there is a subset of XOR 0 that's not empty, then we know that there exists one vector that is a linear an XOR combination of the other ones. That's what it looks like. Any questions on that? So that's one Matroid, but that doesn't solve the problem. Quinn?
You can make the boxes the colors, and
Okay.
you need to have it all colors.
Yeah, exactly. So you could color this one a single color, color this one another color, color all these guys the same color, color all these guys the same color, and now we have an intersection of the XOR linear Matroid and the colorful Matroid. And yeah, okay. So what does our basis look like? What is the size of our basis? What is the size of our basis? Zach?
Well, we want it equal to the total number of boxes, including both players' boxes.
Yes, exactly, and that's what's key. Because somebody observed that if you have, if Alice already has a subset, or if Alice already has stuff that has a subset of XOR 0, then you lose. So you need to make sure that Alice's picks are in there. And you can just do that by making a box with only one element in it, which is a color with only one element in it. And if you need to have every color, then you're forced to take that element. So you have to do that. Yeah, and so your basis has all the distinct colors, and hopefully it's also linearly independent. Any questions on this problem? All right, so this is pretty cool. Another problem that I quite like is Alice and Bob are playing a game. They're gaming. And this time, Alice and Bob, they're both coin collectors. They get around, they like to go to different countries, collect different coins. And Alice she's a generous person, so she has gone and she's made some envelopes each envelope has 2 coins in them, and we'll just like label the coins by like what color what country they're from. And Alice is going to give these envelopes to Bob in pairs. So in each round of the game, she's going to give you 2 envelopes, and you get to pick like one of the envelopes or neither of the envelopes. And you need to make sure that at the end, you've picked some envelopes, and that's pretty cool. That means you get to like keep these coins. But Alice is she's very tricky, and if she's able to find a subset of the envelopes that you chose, such that every country has an even number of coins in like this, like on the envelopes that you have, then actually you don't get any coins. You lose. And you want to maximize the number of coins that you get, which is also the same as maximizing the number of envelopes that you get, because each envelope has exactly 2 coins. So if we have like, if the first round of the game looks like 1, 2, like 1, 3, and the second round of the game looks like, I don't know, it just looks like 2, 2, and 1, 3, whatever. Then like, we can't pick this envelope, because no matter what we do, like she could just throw out everything except this envelope, and now every country has an even number of coins. We also can't like pick both of these envelopes, because now every country is going to have an even number of coins. 0 is even, so okay, that's the game. Spoiler alert: Matroid Intersection. Any ideas, Zach?
I mean, isn't the idea of like checking if there's an even number of countries similar to the XOR?
Yeah, but the numbers themselves go up to like 10 to the 5th or whatever.
No.
I mean, you could coordinate compress, but they're still bigger than like XOR can handle.
Can we do something similar to what's in green, where like I'm just thinking of Arup's example of pulling programming team members. Like we want the number of people from each team to be even.
Well, that's not what this is saying. It's like the number of people from each. It's you have some subset of the ground set, and you need to make sure that the intersection of that subset with each of these like partition subsets is exactly or is less than or equal to 1 element. So either 1 element or 0 elements. This is the colorful Matroid, remember? Cam.
What is the restriction again about the evenness?
So we can't, like, if we pick some envelopes, so for example, let's say that in the first round I pick this envelope, in the second round I pick this envelope, it can't be true that all countries have an even number of coins. Like, so all numbers show up an even number of times. For any subset of the envelopes that you chose. You're also allowed to choose no envelope from like a certain round. So like, if I like another round where it's like 1, 1, and 1, 1, then I can just say, I don't want either of those envelopes. Those guys are going to screw me over, so I'm just going to pass on this round. And we're given the entire state of the game. Like, we don't have any, like, we know all the, like, rounds, so it's not like we're, like, doing an interactive problem. 1. Because if you pick the envelope 1, 1, then no matter what you pick, there is a subset of envelopes that contains an even number of coins per country, because that one envelope, if she throws away everything, now you have 2 coins from one country and 0 coins from the rest.
Wait, is there any subset of the envelopes have that?
Yes, per country. Any subset of the envelopes such that all countries have an even number in all, like in the like sum of all these envelopes. So when we take like 1, 2, and 1, 3, then our frequency array looks like 1, 2, 3. Our frequency array looks like 2, 1.
So you want those to be edges in a graph.
Yes. Okay. So what Arup said is, you notice that there's 2 coins in each envelope. Kind of sounds like an edge. So let's go ahead and draw a graph that looks like this. So we have like country 1, country 2, and country 3. And let's go ahead and label the envelopes as well. This is envelope 1, 2, 3, 4, 5, 6. So then envelope 1 looks like this. Envelope 2 looks like this. Envelope 3 looks like this. Envelope 4 looks like this. 5 looks like this. And 6 looks like this. 1, 2, 3, 4, 5, 6. Okay. So there is a bijection between sets of envelopes that have this like bad property of all things are even, and some property of graphs. Any ideas about the property of a graph? Danny?
Oh, I was just gonna say that maybe we don't care about doing this, but we can get rid of self loops and I think multi-edges as well. Because like
Yeah, self loops are easily we can easily discard those, but let's not. We don't really have to. Why multi-edges?
Cause you can, if you take both.
Yeah, here's the you actually can't get rid of multi-edges. Because maybe one of them, like maybe there's like two envelopes, or like there's like two of the same edge, but like you want to take like one thing from the one round. So like if you had like, it's like this, right? If you deleted like the optimal solution is to pick these two, because you get 4 coins in total. But if you deleted multi-edges and you did this with impunity, you might have deleted this edge. In which case you can't pick both of these at the same time because they're in the same round. Right? So you need to keep the multi-edges. Because there's something about them that's they are different. Zach?
Because they come from different envelopes.
Yeah.
Well, it's like invalid if you have a cycle, since if you like draw that cycle and take like the edges, then each of the elements is taken exactly twice, basically.
Yep. Any questions about that? Should I repeat it, or are we all good?
Like, it's fine the cycle like loops in on itself because you know each one will be like taken twice anyway. Like
Yeah.
an even number of times.
Any cycle, like so, if it does simple cycle or not, any cycle.
Any cycle.
Any cycle. And if it's not a simple cycle, then there exists a subcycle of that cycle that is simple. So, Jake.
And just to reiterate, the condition that we're trying to avoid is that there's a subset of the envelopes that we've taken such that every country in that subset occurs an even number of times.
Every country in the world, 0 is even, so.
Sure. Okay, so that's like, okay, so it needs to be a cycle.
Yeah, it needs to be a cycle. That would be bad if it were a cycle, because then every country would be even, because, like Zach pointed out.
So she has to be unable to find a cycle.
Yes. Okay, well we still haven't solved the problem. Because we can find a spanning tree of this graph, but like not every spanning tree is valid. So on.
Just to confirm, from every country we can select 2, 1 or neither envelope?
No, from each round we can select one of the envelopes or neither of the envelopes. Sachin?
Assign each of the rounds a color and then its intersection of graph.
Yep. So assign each of the rounds a color, and then it's the intersection of the graphic matroid, where you like draw the edges like this, and the colorful matroid, where like the color of each edge is what round it's in. So then you can't take 2 things from the same color, because that would be taking 2 things from the same round, which you're not allowed to do. But everything else is satisfied. Anyone?
What are the bounds on this problem?
It's like 400 or something like that. So Matroid Intersection, it really depends on the like Matroid itself. Like this Matroid is super easy to maintain because all you need is an array. This Matroid is like kind of hard to maintain because it's not hard. It's like harder to maintain than it is to maintain this, because you have to have like all the vectors, and so like checking if I can add something to the set or just actually adding it to the set requires like a non-constant amount of like checking time, right? And also like the graphic Matroid requires a DSU and stuff like that. The runtime is pretty complicated, but oftentimes like we can just boil it down to cubic and go from there. So yeah, it's like n cubed roughly, and that's why n is 400 in this problem.
Do all like of these Matroid intersection problems basic? They all just use that same idea that you used for the first problem with the theorem that you didn't prove.
Yeah, it's like
So we can generalize to that
what's up?
every time. We can generalize to that every time. We don't actually have to think about the Matroid properties themselves.
Well, like we have to be able to maintain these matroids. Like we have to be able to add, like in this problem, we have to maintain a DSU and an array of colors, and like a frequency array of colors.
But the algorithm is for all Matroids.
The algorithm works in general for any 2 matroids.
But then how you draw
rounds.
the colors of the edges is based on the specific problem.
Yeah, like how you determine which elements
Whether or
are
not
in
you can add
Y1 and
it.
Y2 is up to implementation.
It's like a hack pack where it's like you define a matroid where like you make like 2 functions where you can add an element or you can like check to see if an element can be added.
And also
like the
clear.
black
And
box.
also clear. You have to be able to clear, which is usually easy.
Is that
but-
in count?
well, it technically is. Like I think it's on a branch of Cactal, but yeah, I have code for it. I've used it. It's actually pretty simple to use. Like,
Why is the colorful Matroid helpful in this particular problem?
so we weren't allowed to take 2 envelopes from the same round. So that's like the same as saying
So
let's
rounds
color.
have colors.
Yeah, each round has a unique color, and both envelopes in that round have the same color. So the colorful Matroid lets us guarantee that we don't take 2 of the same thing. By the way, we can extend the colorful Matroid to, instead of 1, it's less than or equal to C. It's like also a Matroid. So the colorful Matroid is a special case where C equals 1. But you can also do like, I can have up to 5 of the same color, and that's also a matroid. That's the proof is the same thing. Okay?
Can you extend it to some lower bound?
What? That is a low. What?
It's like
Oh, you have to have at least.
Yeah.
No, because try to maintain this property when you do that,
Oh.
right?
They all have
so,
to go to 0.
So Cam is asking, can we do this? Right? Cam is asking, can we do this? The answer, in a second. The answer is no, because by the hereditary property, by the way, the empty set is always independent. The empty set must always be an element of this, because otherwise the hereditary property would be violated. But the independent set, you're going to be hard pressed to find out how the independent set can have a lower bound of number of colors.
I think you just take like
The complement?
the complement, yeah.
Well, then you just
Yeah, I was thinking.
converted this back to the normal color.
Yeah.
Exactly, that's what I'm saying.
Well, you can
always
only do
right?
that if every partition is the same size, right? Like taking that complement and just seeing which elements you exclude.
Yep.
Probably.
That's like then it's like a circuit, and that's it.
Yeah,
You can't like intersect that anymore. You can't complement.
Really?
Well, like, it's just this, but instead of
It's like
tracking
it's a different
elements-
Matroid. But if you can prove it to be Matroid, then sure.
But it's the same ground set, so it should
Yeah,
be fine.
same ground set. The key is you can't intersect Matroids with different ground sets because what's
So
Oh.
But you're grounded.
it's super important that we can take care of that in this process.
yeah, because taking exactly one.
Right.
Yeah. Okay, there's some other problems, but
Any other questions on this one? Otherwise, if you have others, you post in the chat.
Yep.
The King's Guards.
Good. This is a good lecture.
Did that work?
Do you have
Act 21.
do you have like sources for like further
Any-
reading and problems?
Yeah, if you Google Matroid Intersection code forces, there's like a really long but pretty cool like tutorial on it. It's kind of nice.
All right. I need to talk to Save and Quinn briefly on their way out. Otherwise, we're going to 119 for lunch and festivities.